Hello everyone, I am Sham Parikh. I am a student of BSc Chemistry Honours first year. My roll number is 10 and today we are going to read the chapter Thermodynamics from the NCERT book. Let us start. So, it is the only physical theory of universal content concerning which I am convinced that within the framework of the applicabilities of its basic concept it will never be overthrown. So this statement was given by Albert Einstein. Chemical energy stored by molecules can be released as heat during chemical reaction when a fuel like methyl cooking gas or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine or to provide electrical energy through a galvanic cell like dry cell. Thus various forms of energy are interrelated and under certain conditions this may be transformed from one form into another. The study of this energy transformation forms the subject matter of thermodynamics. The law of thermodynamics deal with energy changes of macroscopic system involving a large number of molecules rather than microscopic system containing a few molecules. Thermodynamics is not concerned about how and at what rate this energy transformation are carried out, but is based on initial and final state of a system undergoing the changes. Laws of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some important question through thermodynamics. Like how do we determine the energy change involved in a chemical reaction, what drives a chemical reaction, to what extent do chemical reactions proceed. Thermodynamic matter terms. We are interested in chemical reactions and the energy changes accompanying them. For this we need to know certain thermodynamics terms. These are discussed below. The system and surrounding. A system in the thermodynamics refer to part of universe in which observations are made and remaining universe constitute the surrounding. The surrounding includes everything other than system. The universe equals to the system plus the surrounding. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, all the particular purposes, the surroundings are that portion of the remaining universe which can interact with the system. Usually, the region of space in the neighborhood of the system constitutes surrounding. For example, if we are studying the reaction between two substances A and B, the beaker containing the reaction mixture is the system and the room where the beaker is kept is the surrounding. Note that the system may be defined by physical boundaries like beaker or test tube, or the system may simply be defined a set of Cartesian coordinates specifying a particular volume in a space. This is designed to allow us to control and keep track of all movement of matter and energy in or out of the system. Type of system. There are the types of system are open system. In an open system, there is exchange of energy and matter between system and surrounding. The presence of reactant in an open beaker is an example of open system. Closed system. In a closed system, there is no exchange of matter, but exchange of energy is possible between system and the surrounding. The presence of reactants in a closed vessel is such example of closed system. Isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surroundings. The presence of reactants in a thermos, flask or any other closed insulated vessel is an example of an isolated system. The state of the system. The system must be described in order to make any useful calculation by specifying quantitatively each of the properties such as its pressure P, volume V, the temperature T, as well as the composition of the system. We need to describe the system by specifying it before and after the change. We would like to recall from our physics course that the state of a system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of the state is introduced. It does not need detailed knowledge of motion of each particle because we deal with average measurable properties. We specify the state of the system by state functions and state variable. The state of a thermodynamic system is described by its measurable or macroscopic properties. We can describe the state by quoting its pressure, volume, temperature, amount, etc. Variable like pressure, volume, temperature are called state variable or state function because their values depend only on the state of the system and not on how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. In thermodynamics, we call the internal energy U of the system, which may change when heat passes into or out of the system. Work is done on or by the system. Matter enters or leaves the system. The systems are classified accordingly. Work. Let us first examine a change in internal energy by doing work. We take a system containing some quantity of water in a thermos flask or in an insulated beaker. This should not allow exchange of heat between the system and surroundings, though it's through its boundary, and we call this type of a system and adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and surrounding. Here the wall separating the system and the surrounding is called the adiabatic wall. Let us bring the change in the internal energy of the system by doing some work on it. Let us call the initial state of the system as state A and its temperature as TA. Let the internal energy of the system in state A be called UA. We can change the state of the system in two different ways. One way, we do some mechanical work, say 1 kilojoule, by rotating a set of small paddles and thereby churning water. Let the new state be called B and its temperature as TB. It is found that TB is greater than TA and the change in temperature is TB minus TA, which is delta T. Let the internal energy of the system in state B be UB and the change in internal energy delta U equals to UB minus UA. Second way, we now do an equal amount electrical work with the help of an immersion rod and note down the temperature changes. We find that the change in temperature is same as in the earlier case, say TB minus TA. In fact, the experiment in the above manner were done by J.P. Joule between 1840 to 1850, and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produces the same change of state as measured by the change in the temperature of the state. So it seems appropriate to define a quantity, the internal energy U, whose value is characteristic of the state of a system, whereby the adiabatic work WAD required to bring about a change of state is equal to the difference between the value of U in one state and that in another state, delta U, that is delta U equal to U2 minus U1 equal to work adiabatic. Therefore, internal energy U of the system is a state function. By conventional of IUPAC in chemical thermodynamics, the positive sign expresses the work adiabatic is positive when work is done on the system and the internal energy increases. Similarly, the work is done by the system, work adiabatic will be negative because internal energy of the system decreases. Can we name some other familiar state functions? Some of other familiar functions are volume, pressure, and temperature. For example, if we bring a change in temperature from 25 degree to 35 degree, the change of temperature is plus 10 degree. Wherever we go straight up to 35 degrees Celsius or we cool the system for a few degree, then the system to the final temperature. Then take the system to the final temperature. This T is a state function, and the change in temperature is independent of the routine taken. B, heat. We can also change the internal energy of a system by transfer of heat from the surroundings to the system or vice versa without expenditure of work. This exchange of energy, which is the result of temperature difference, is called heat, Q. Let us consider bringing about the same change in temperature, the same initial and final state as before by transfer of heat through thermally conducting walls instead of adiabatic walls. We take water as temperature TA in a container having thermally conducting walls, say made up of copper, and enclose it in a huge heat reservoir at temperature TB. The heat absorbed by the system water Q can be measured in terms of temperature difference TB minus TA. In this case, change in internal energy delta U equal to Q when no work is done at constant volume. By conventions of IUPAC in chemical thermodynamics, the Q is positive when heat is transformed from the surrounding to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surrounding, resulting in decrease of internal energy. The general case. Let us consider the general case in which a change of state is brought about both by doing work and by transfer of heat. We write change in internal energy for these cases delta U equal to Q plus W. For a given change in state, Q and W can vary depending on how the change is carried out. However, Q plus W equals to delta U will depend only on initial and final stage. It will be independent on the way of the change is carried out. If there is no transfer of energy as heat or as work, if W equal to if 0 and Q equal to 0, then delta U equal to 0. The equation delta U equal to Q plus W is mathematical state of the first form of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy, that energy can either be created or destroyed. Note, there is considerable difference between the character of the thermodynamic property energy and that of a mechanical property such as volume. We can specify an unambiguous value for volume of a system in a particular state, but not the absolute value of the internal energy. However, we can measure only the changes in the internal energy of the system. Application. Many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them. Work. First of all, let us concentrate on the nature of work a system can do. We will consider only mechanical work, that is pressure volume work. For understanding pressure volume work, let us consider a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas is V and pressure of the gas inside is P. If external pressure is Px, which is greater than P, piston is moved inward till the pressure inside becomes equal to P external. Let this change be achieved in a single step and the final volume be Vf. During this compression, suppose piston moves a distance L and its cross-sectional area is A. Then volume change is equal to L cross A, which gives us delta V, which is V final minus V initial. We also know pressure equal to force upon area. Therefore, force of piston equal to P external into area. If W is work done by moment of piston, then work equal to force into distance, which is P external into A dot L, P external into minus delta V equal to minus delta P external, delta V equal to minus P external or Vf minus Vi. The negative sign of expression is required to obtain conventional sign for W, which will be positive. It indicates that in case of compression, work is done on the system. Here Vf minus Vi will be negative and negative multiplied by negative will be positive. Hence the sign will be positive. If the pressure is not constant at every stage of compression but changes in number of finite steps, work done on the gas will be summed over all the steps and will be equal to summation of delta P delta V. If the pressure is not constant but changes during the process, such that it is always infinitesimally greater than the pressure of the gas, then at each stage of compression the volume decreases by an infinitesimal amount dV. In such a case, we can calculate the work done on the gas by the relation W equal to minus integration Vi to Vf P external into dV. Here P external at each stage is equal to P initial plus dP. In case of compression in an expansion process under similar condition, the external pressure is always less than the pressure of the system, that is P external. That is P external equal to P initial minus dP. In general case, we can write P external equal to P initial plus minus dP. Such processes are called reversible processes. A process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed at an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surrounding are always in near equilibrium with each other. Processes other than reversible processes are known as irreversible processes. In chemistry, we face problems that can be solved if we relate the work term to the internal pressure of the system. We can relate work to internal pressure of the system under reversible condition by writing equation V reversible to minus integration V initial to V final P external dV equals to minus integration V initial to V final P initial plus minus dP multiplied by dP. Since dP cross dV is very small, we can write work reversible equal to minus integration V initial to V final P initial dV. Now the pressure of the gas P initial, which we write as P now, can be expressed in terms of its volume through gas equation, that is PV equal to nRT. So P equals to nRT upon V. Therefore at constant temperature, V reversible equal to minus integration V initial to V final nRT dV upon V, which gives us minus nRT initial V final upon V initial, or it gives us minus 2.303 nRT log V final upon V initial. Free expansion of gas in vacuum, P external equals to 0 is called free expansion. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Now we can write equation 5.1 in number of phases depending on the type of process. Let us substitute W equal to minus P external delta V in equation 5.1 and we get delta U equal to Q minus P external delta V. If a process is carried out at constant volume delta V equal to 0, then delta U equal to KV. The subscript V in QV denotes that heat is supplied at constant volume. Isothermal and free expansion of an ideal gas. For isothermal, T equal to constant expansion of an ideal gas into vacuum W equal to 0. Since P external equal to 0, also Joule determined experimentally that Q equal to 0, therefore delta U equal to 0. Equation 5.1 delta U equal to Q plus W can be expressed for isothermal, irreversible and reversible changes as follows. For isothermal irreversible changes, Q equal to minus W equal to P external V final minus V initial. For isothermal reversible change, Q equal to minus W equal to nRT ln Vf upon Ve, which gives us 2.303 nRT log V final upon V initial. For adiabatic change, Q equal to 0, delta U equal to V adiabatic. Enthalpy H. A useful new state function. We know that the heat absorbed at a constant volume is equal to change in the internal energy, that is Q delta U equal to QV. But most of chemical reactions are carried out not at constant volume but in flask or test tube under constant atmospheric pressure. We need to define another state function which may be suitable under this condition. We may write equation delta Q equal to Qp minus P delta V at constant pressure, where Qp equal to Qp is heat absorbed by the system and minus P delta V represent the expansion work done by the system. Let us represent the initial state by subscript 1 and final state by 2. We can rewrite the above equation as U2 minus U1 equal to Qp minus P V2 minus V1. On rearranging we get Qp equal to Q2 plus P V2 minus Q1 plus P V1. Now we can define another thermodynamic function, the enthalpy H, Greek word enthalpian, to warm or heat content, as H equal to U plus PV. So equation becomes Qp equal to H2 minus H1 equal to delta H. Although Q is path dependent function, H is a state function because it depends on U, P and V, all of which are state functions. Therefore delta H is independent of path, hence Qp is also independent of path. For infinite changes at constant pressure, we can write delta is equal to delta U plus P delta V delta PV. Since P is constant, we can write delta is equal to delta U plus P delta V. It is important to note that when heat is absorbed by the system at constant pressure, we are actually measuring changes in the enthalpy. Remember, delta is equal to Qp, heat absorbed by the system at constant pressure. Delta H is negative for exothermic reaction which involve heat during the reaction, and delta H is positive for endothermic reaction which absorb heat from the surrounding. At constant volume, delta V equal to 0, delta Q equal to Qv. Therefore equation becomes delta is equal to delta U equal to Qv. The difference between delta H and delta U is not usually significant for systems consisting of only solids and liquids. Solids and liquids do not suffer any significant volume change upon heating. The difference, however, becomes significant when gases are involved. Extensive and intensive properties. In thermodynamics, a distinction is made between extensive properties and intensive property. An extensive property is a property whose value depends on the quantity of size or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. Those properties which do not depend on the quantity of size or matter are called intensive property. For example, temperature, density, pressure, etc. A molar property xm. Chi m is the value of an extensive property chi of the system for 1 mole. If n is the amount of matter, chi m equal to chi upon n is independent of the amount of matter. Other example are molar volume Vm and molar heat capacity Cm. Let us understand the distinction between extensive and intensive property by considering a gas enclosed in a container of volume V and a temperature T. Let us make a partition such that volume is half. Each part now has half of the origin volume V by 2, but the temperature will still remain the same T. It is clear that volume is extensive property and temperature is intensive property. Heat capacity. In this subsection, let us see how to measure heat transfer to a system. This heat appears as a rise in temperature of the system. In case of heat absorbed by the system, the increase of temperature is proportional to the heat transferred. Q equal to coefficient into delta T. The magnitude of coefficient depends on the size, composition and nature. We can write Q as C delta T. The coefficient C is called heat capacity. When C is larger, given amount of heat result in only small temperature rise. Water has a large heat capacity. There is a lot of energy needed to raise its temperature. C is directly proportional to the amount of substance. The molar heat capacity is Cm equal to C upon n is the heat capacity for 1 mole of substance, and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. For finding out the heat Q required to raise the temperature of a sample, we multiply the specific heat of the substance C by the mass m and temperature change delta T as Q equal to C cross m dot cross delta T C delta T. The relationship between Cp and Cv for an ideal gas at constant volume, the heat capacity C is denoted by Cv, and at constant pressure this is denoted by Cp. Let us find the relationship between the two. We can write equation for heat Q. At constant volume, Q equal to Cv delta T delta U. At constant pressure, Qp Cp delta T delta H. The difference between Cp and Cv can be derived from ideal equation. Delta is equal to delta U plus R delta T. On putting the value of delta H and delta U, we have Cp delta T equal to Cv delta T plus R delta T. Cp equal to Cv plus R. Cp minus Cv equal to R. Measurement of delta U and delta H calorimetry. We can measure energy changes associated with chemical or physical process by an experiment technique called calorimetry. In calorimetry, the process is carried out in vessel called calorimeter, which is immersed in a known volume of liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine the heat evolved in the process by measuring temperature changes. This can be done by two processes. Delta U measurement for chemical reaction, heat absorbed at constant volume is measured in a bomb calorimeter. Here a steel vessel is immersed in water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surrounding. A combustible substance is burnt in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change. That is, the energy changes associated with reactions are measured at constant volume. Under this condition, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as V equal to 0. Temperature changes if the calorimeter produced by the completed reaction is converted to QB by using known heat capacity of the calorimeter. Delta H measurement. Measurement of heat changes at constant pressure. Measurement of heat change at constant pressure can be done in calorimeter. We know that delta is equal to Qp at constant pressure, and therefore heat absorbed or evolved. Qp at constant pressure is also called the heat of reaction or enthalpy of reaction. In an exothermic reaction, heat is evolved and system loses heat to the surrounding. Therefore, Qp will be negative and delta H will also be negative. Similarly, in an endothermic reaction, heat is absorbed, Qp is positive and delta H will be positive. Enthalpy change, delta H of a reaction enthalpy. In a chemical reaction, reactants are converted into products and is represented by reactant gives product. This enthalpy change accompanying a reaction is called reaction enthalpy. The enthalpy change of a chemical reaction is given by the symbol delta H. Delta RH, delta R is sum of enthalpy of product minus sum of enthalpy of reactants. Here symbol sigma is used for summation, and AI and AB and BI are the stoichiometric coefficient of the product and reactant respectively in the balanced chemical equation. Enthalpy change is very useful quantity. Knowledge of this quantity is required when one needs to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. Standard enthalpy of reaction. Enthalpy of reaction depends on the condition under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in standard states. The standard state of a substance at a specific temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. Standard state of liquid iron at 500 Kelvin is pure iron at 1 bar. Usually data taken at 298 Kelvin. Similarly, standard conditions are denoted by adding the superscript to the symbol delta H. Example delta H. Enthalpy of changes during phase transformation. Phase transformation is also involved energy changes. Ice, for example, requires heat for melting. Normally, this melting takes place at constant pressure, and during phase change, temperature remains constant. Here, delta fuse H is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surrounding. The enthalpy change that accompanies melting of 1 mole of solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Melting of solid is endothermic, so all enthalpies of fusion are positive. Water requires heat for evaporation at constant temperature of its boiling point Tb and at constant pressure. H2O liquid equal to H2 gas. Delta vaporization H equal to plus 40.79 kilojoule mole inverse. Delta V vaporization H minus is the standard enthalpy of vaporization. Amount of heat required to vaporize 1 mole of liquid at constant temperature and under standard pressure is called its standard enthalpy of vaporization or molar enthalpy of vaporization. Sublimation is directly conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 198 Kelvin with delta sublimation H equal to 25.2 kilojoule mole inverse. Naphthalene sublimes slowly, and for this delta sublimation H to 73.0 kilojoule mole inverse. Standard enthalpy of sublimation is the change in enthalpy when 1 mole of solid substance sublimes at a constant temperature and under standard pressure 1 bar. The magnitude of the enthalpy change depends on the strength of the intermolecular interaction of the substance undergoing the phase transformation. Thus, it requires less heat to vapor 1 mole of acetone than it does to vaporize 1 mole of water. Table gives a value of standard enthalpy changes of fusion and vaporization for substance. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of compound from its element in their most stable state of aggregation, also known as reference state, is called standard molar enthalpy of formation. Its symbol is delta F in the bottom H, where the subscript F indicates that 1 mole of compound in question has been formed in its standard state from its element in the most stable state of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen is H2 gas, and those of dioxygen, carbon and sulfur are O2 gas, C graphite and C rhombic respectively. Some reaction with standard molar enthalpy of formation are as follows: H2 plus half O2 equal to H2O, delta FH equal to minus 285.8 kilojoule mole inverse. C graphite plus 2H2 equal to CH4 gas. It is important to understand that the standard molar enthalpy of formation delta H is just a specific case of delta RH, where 1 mole of a compound is formed from its constituent elements, as in the above three equations, where 1 mole of each water, methane and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction is not an enthalpy formation of calcium carbonate, since calcium carbonate has been formed from other compounds and not from its constituent elements. Also, for the reaction given below, enthalpy change is not standard enthalpy formation. Here 2 moles instead of 1 mole of the product is formed from the elements. Therefore, by dividing all coefficient in the balanced equation by 2, expression for enthalpy of formation of HBr is written as half H2 plus half Br equal to HBr. Standard enthalpy of formation of some common substances are given. By convention, standard enthalpy for formation delta HF of an element in reference state, that is in its most stable state of aggregation, is taken as 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide with all the substance in the standard states. We can make use of standard enthalpy of formation and calculate the enthalpy change for the reaction. The following general equation can be used for the enthalpy change: delta HR equal to sigma I AI delta FH products equal to minus sigma I BI delta FH reactants. Where A and B represent the coefficient of product and reactants in the balanced equation, let us apply the above equation for decomposition of calcium carbonate. Here coefficient A and B are 1 each. Therefore, delta RH equal to delta FH equal to CaOS plus delta FH CO2 gas minus delta HF CaCO3, which gives us 178.3 kilojoule mole inverse. Thus, the decomposition of CaCO3 is an endothermic process, and you have to heat it for getting the desired product. Thermochemical equation: a balanced chemical equation together with the value of its delta RH is called a thermochemical equation. We specify the physical state along with allotropic state of the substance in an equation. For example, C2H5OH in liquid state plus 3O2 in gaseous state plus 2CO2 in gaseous state plus 3H2 in liquid state. Delta H R is minus 1367 kilojoule mole inverse. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. It would be necessary to remember the following convention regarding thermochemical equation. The coefficient in a balanced thermochemical equation refer to the number of moles, never molecules of a reactant and products involved in the reaction. The numerical value of delta RH refers to the number of moles of substance specified by an equation. Standard enthalpy change delta HR will have units as kilojoule mole inverse. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction: Fe2O3 plus 3H2 gives us 2Fe plus 3H2O. From the table of standard enthalpy of formation, we find delta HF is minus 285.83 kilojoule mole inverse for H2O. For delta HF Fe2O3 it is minus 824.2 kilojoule mole inverse. Also delta HF for Fe and S is 0, and delta HF for H2 is also 0 as per convention. Then delta H F equal to 3 into minus 285.85 kilojoule mole inverse minus 1 into minus 824.2 kilojoule mole inverse, which gives us minus 33.3 kilojoule mole inverse. Now that the coefficient used in this calculation are pure numbers which are equal to the respective stoichiometric coefficient, thus the unit of delta RH is kilojoule mole inverse, which means per mole of reaction. Once we balance the chemical equation in a particular way as above, this defines the mole of reaction. If we had balanced the equation, for example, half Fe2O3 plus 3 by 2 H2 equal to Fe plus 3 by 2 H2O, then this amount of reaction would be 1 mole of reaction, and delta RH would be minus 16.6 kilojoule mole inverse. It shows that enthalpy is an extensive quantity. When a chemical equation is reversed, the value of delta H is reversed in sign. For example, N2 plus 3H2 equal to 2NH3, delta RH is minus 91.8 kilojoule. Plus or 2NH3 equal to N2 plus 3H2, it is plus 91.8 kilojoule mole inverse. Hess law of constant heat summation. We know that enthalpy is a state function, therefore the change in enthalpy is independent of the path between initial state and final state. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in series of steps. This may be stated as following in form of Hess law. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of standard enthalpy of the intermediate reaction into which the overall reaction may be divided at the same temperature. Let us understand the importance of this law with the help of example. Consider the enthalpy change for the reaction C, that is in graphite form, solid, plus half O2 gives us CO gas, delta RH is question mark. Although CO gas is the major product, some CO2 gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, we can find some other reaction involving related species. It is possible to calculate the enthalpy change for the above reaction. Let us consider the following reactions. C graphite plus O2 gives us CO2, for which delta H is minus 393.5 kJ mole inverse. CO plus half O2 gives us CO2, and for this delta H is minus 283.0 kJ mole inverse. We can combine the above two reactions in such a way as to obtain the desired reaction. To get 1 mole of CO1 on the right, we reverse equation in this. Heat is absorbed instead of being released, so we change sign of delta R value. CO2 gives us CO plus half O2, and for that delta H equals to plus 283.0 kJ mole inverse. Adding equation 1 and 3, we get desired equation. C graphite plus half O2 gives us CO, and for which delta HR is minus 110.5 kJ mole inverse. In general, if enthalpy of an overall reaction A gives B along one route is delta RH and delta RH1, RH2, RH3 representing enthalpies of reaction, then delta RH equal to delta RH1 plus RH2 plus continuous. Enthalpy for different types of reactions. It is convenient to give name to enthalpy specifying the type of reaction. Standard enthalpy of combustion. Combustion reactions are exothermic in nature. They are important in industry, rocketry, and other walks of life. Standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion and all the reactants and products being in their standard states at the specific temperature. Cooking gas in cylinders contain mostly butane. During complete combustion of 1 mole of butane, 2658 kJ of heat is released. We can write the thermochemical reaction for this. Se4H10 plus 13O2 gives us 4CO2 plus 5H2O, and for this heat of combustion is minus 2658.0 kJ mole inverse. Similarly, combustion of glucose gives out 2802.0 kJ per mole of heat, for which the overall equation is C6H12O6 plus 6CO2 gives us 6CO2 plus 6H2O. Delta CH is minus 2802.0 kJ mole inverse. Our body also generates energy from food by the same overall process as combustion, although the final products are produced after a series of complex biochemical reactions involving enzymes. Enthalpy of atomization. Consider the following example of atomization of dihydrogen. H2 gives us 2H, and for the enthalpy of atomization is 435.0 kJ mole inverse. You can see that H atoms are formed by breaking hydrogen-hydrogen bond in dihydrogens. The enthalpy change in this process is known as enthalpy of atomization. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecule, the dihydrogen, the enthalpy of atomization is also the bond association enthalpy. The other example of enthalpy of atomization can be CH4, which gives us C hydrogen plus 4 C gas plus 4 hydrogen in gaseous state, and for the enthalpy of atomization is 1665 kJ mole inverse. Note that the products are only atoms of carbon and hydrogen in gaseous phase. Now see the following reaction. Sodium S plus sodium G gives an enthalpy of atomization is 108.4 kJ mole inverse. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. Bond energy symbol delta bond H. Chemical reaction involve the breaking and making of chemical bonds. Chemical reactions involve the breaking and making of chemical bonds. Energy is required to break a bond, and energy is released when a bond is formed. It is possible to relate heat of reaction to changes in energy associated with breaking and making of chemical bond with reference to the enthalpy changes associated with chemical bonds. Two different terms are used in thermodynamics: bond dissociation enthalpy, mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecule. Diatomic molecule. Consider the following process in which bonds in 1 mole of dihydrogen are broken. The enthalpy change involved in this process is the bond dissociation enthalpy of hydrogen-hydrogen bond. The bond dissociation enthalpy is the change in enthalpy enthalpy when one mole of covalent bond of a gaseous covalent compound is broken to form products in the gas phase. Note that it is the same as the enthalpy of atomization of dihydrogen. This is true for all diatomic molecules. For example, Cl2 gives us to Cl, and for that and for that bond enthalpy is 242 kilojoule mole inverse, and for similarly for oxygen it is 428 kilojoule mole inverse. In this case of polyatomic molecule, bond dissociation enthalpy is different for different bonds with the same molecule. Polyatomic molecule. Let us now consider a polyatomic molecule like methane CH4. The overall thermochemical equation for its atomization reaction is CH4 gives us C plus 4H, and for the bond enthalpy is 1665 kilojoule mole inverse. In methane, all the 4 CH bonds are identical in bond length and energy. However, the energies required to break the individual CH bond in each successive step differ. CH4 gives us CH3 plus H, and for this bond enthalpy is plus 427 kilojoule mole inverse. CH2 plus H gives us, and with bond enthalpy 439 kilojoule mole inverse. CH2 gives us CH plus H, and for that bond enthalpy 452, and CH gives us C plus H, and for that bond enthalpy 347. And therefore CH4 gives us C plus 4 hydrogen. Bond enthalpy is 1665 kilojoule mole inverse. In such a case, we use mean bond enthalpy of CH bond. We find that mean CH bond enthalpy in methane is 416 molejoule inverse. It has been found that mean CH bond enthalpy differ slightly from compound to compound, as in CH3, CH2, Cl, CH3, and etc., but it does not differ in great deal. Using Hess law, bond enthalpy can be calculated. Bond enthalpy varies from some single and multiple bonds are given in table. The reaction enthalpies are very important quantities, as this arise from the changes that accompany the breaking of old bonds and formation of the new bonds. They can predict enthalpy of reaction in gas phase. If we know different bond enthalpies, the standard enthalpy of reaction is related to bond enthalpy of the reactants and products in gas phase reaction. This relation is particularly more useful when the required value are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecule minus the amount of energy required to break all the bonds in the product molecule. Lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change which occurs when one mole of an ionic compound dissociates into its ion in gaseous state. Since it is impossible to determine lattice enthalpies directly by experiment, we use an indirect method where we construct an enthalpy diagram called Born-Haber cycle. Let us now calculate the lattice enthalpy of Na positive Cl negative by following steps given below. NaS gives us Na in gaseous form. Sublimation of sodium atom, and for the sublimation energy is 108. Enthalpy of sublimation is 108.4 kilojoule mole inverse. And Na gas gives us Na positive plus 1 electron, the ionization sodium atom, and for this enthalpy is ionization enthalpy is 496 kilojoule mole inverse. And half Cl2 gives us chlorine gas, the dissociation of chlorine. The reaction enthalpy is half the bond dissociation energy, and for that the bond enthalpy is 121 kilojoule mole inverse. Chlorine plus 1 electron gives us chlorine negative, electron gained by chlorine atom. The electron gain enthalpy is minus 348.6 kilojoule mole inverse. We have learned about ionization enthalpy and electron gain enthalpy. In fact, these terms have been taken from thermodynamics. Earlier terms, ionization energy and electron affinity, were in practice in place of the above terms. Now, Na positive plus Cl negative gives us Na positive plus Cl. The sequence of steps is shown in figure 5.9 and is known as Born-Haber cycle. So, in this, the importance of the cycle is that the sum of enthalpy changes around the cycle is 0. Applying Hess law, we get delta H lattice 411.2 plus 108.4 plus 121 plus 496 minus 348, and we get as plus 788 kilojoule mole inverse, and this is the enthalpy for NaCl. Internal energy is smaller than 2 RT because delta Ng is equal to 2 and is equal to plus 780 kilojoule mole inverse. Now we use the value of lattice enthalpy to calculate enthalpy solution from expression. For 1 mole of NaCl, lattice energy is plus 788 kilojoule mole inverse, and delta H is minus 784 from the literature. The dissolution of NaCl is accompanied by very little heat change. Enthalpy of solution. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interaction between the ions are negligible. When an ionic compound dissolves in a solvent, the ions leave their ordered position on the crystal lattice. These are now more free in solution, but solvation of these ions also occur at the same time. This is shown diagrammatically for an ionic compound AB. The enthalpy of solution of AB in water is therefore determined by the selective values of the lattice enthalpy and enthalpy of hydration of ions. For most of the ionic compound, delta S soluble H is positive as the dissociation process is endothermic. Therefore, the solubility of most salts in water increases with rise of temperature. If the lattice enthalpy is very high, the dissolution of the compound may not take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitude of enthalpy change may be made by using table of bond energies and lattice energy, enthalpy of dilution. It is known that enthalpy of solution is the enthalpy change associated with the addition of a specified amount of solute to the specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen chlorine in 10 mole of water can be represented by the following equation. For convenience, we will use the symbol aqueous for water. HCl plus tan aqueous gives us HCl dot tan aqueous. Delta H is minus 69.01 kilojoule per mole. Let us consider the following set of enthalpy change. S1 HCl plus 25 aqueous equal to, and delta H is 70 to minus 72.03 kilojoule per mole. S2 HCl plus 40 aqueous HCl 0.40, delta H is minus 72.79. S3 HCl plus infinite aqueous HCl dot infinite aqueous, delta H is minus 94.85 kilojoule. The value of delta H shows general dependence of the enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches as a limiting value, that is the value in infinitely dilute solution. For hydrochloric acid, this value of delta H is given in equation. If we subtract the first equation S1 from the second equation S2 in the above set of equation, we obtain delta H is minus 0.76 kilojoule mole inverse. This value is enthalpy of dilution. It is the heat withdrawn from the surroundings when additional solvent is added to the solution. The enthalpy of dilution of a solution is dependent on the original concentration of the solution and the amount of solvent added. Spontaneity. The first law of thermodynamics tells us about the relationship between the heat absorbed and the work performed on by a system. It puts no restriction on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon and oxygen given carbon dioxide, but heat will not flow from colder body to warmer body on its own. The gas in a container will not spontaneously contract into one corner. Carbon dioxide will not form and dioxygen spontaneously. These are many other spontaneously occurring changes show unidirectional change. As we may ask, what is the driving force of spontaneous occurring changes? What determines the direction? Let us first understand what do we mean by spontaneous reaction or change. You may think by a common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactant. Take the case of combination of hydrogen and oxygen. This gas may be mixed at room temperature and left for many years without observing any perceptible change. Although the reaction is taking place between them, it is at an extremely slow rate. It is still called spontaneous reaction. So spontaneous means having the potential to proceed without the assistance of external agency. However, it does not tell about the rate of reaction. Another aspect of spontaneous reaction is that this cannot reverse the direction. We may summarize as a spontaneous reaction is an irreversible process and may only be reversed by some external agency. Is decrease in enthalpy a criterion for spontaneity? If, for example, the phenomena like flow of water downhill or fall of stone on the ground, we find that there is a decrease in potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because decrease in energy is taken place, and in case of exothermic reaction, for example, half N2 plus minus H2 gives us NH3, half H2 plus half Cl2 gives us HCl, and for that delta H is minus 92.32 kilojoule mole inverse. H2 plus O2 gives us H2, and for the delta H is minus 25.8 kilojoule mole inverse. The decrease in enthalpy passing from reactants to products may be shown for any exothermic reaction or an enthalpy diagram. Thus, the postulate that drives force a chemical reaction may be due to decrease in sound reasonable as the basic of evidence so far. Now, let us example the following reaction. Half N2 plus O2 gives us NO2, and for that delta H is plus 33.2 kilojoule mole inverse. Graphite plus 2S sulfur gives us CH2, and for that delta H is plus 128.5 kilojoule mole inverse. This reaction, though endothermic or spontaneous, the increase in enthalpy may be represented on an enthalpy diagram. Therefore, it becomes obvious that while decrease in enthalpy may be a contributory factor for spontaneity, but it is not true for all cases. Entropy and spontaneity. Then what drives the spontaneous process in a given reaction? Let us example such a case in which delta H is 0. That is, there is no change in enthalpy but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container which is isolated from the surrounding. The two gases, say gas A and gas B, are represented by black dots and white dots respectively and separated by movable partition. When the partition is withdrawn, the gases begin to diffuse into each other, and after a period, diffusion will be complete. Let us examine the process. Before partition, if we were to pick up the gas molecules from left container, we would be sure that there will be molecule of gas A, and similarly, if we were to pick up the gas molecule from right corner, we would be sure that this will be molecule of gas B. But if we were to pick up molecule from container when partition is removed, we are not sure whether the molecule picked are gas A or gas B. We say that the system has become less predictable and more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for the system energy to become more disordered or chaotic. Then this could be a criteria for spontaneous reaction, spontaneous change. At this point, we introduce another thermodynamic function, entropy, denoted as S. The above mentioned disorder is the manifestation of entropy. To form a mental picture, one can think of entropy as a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is entropy. As far as a chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactant to another. If the structure of the product is very much disordered than that of the reactant, there will be resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated quantitatively by a consideration of the structure of the species taking part in the reaction. Decrease of regulatory in structure would mean increase in entropy for a given substance. The crystalline solid state is the state of lowest entropy. The gaseous state is state of highest entropy. Now let us try to quantify entropy. One way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method, which is beyond the scope of this statement. Other way would be to relate the process to the heat involved in the process, which would make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal energy U and enthalpy H, is a state function, and delta S is independent of path. Whether heat is added to the system, it increases molecular motion, causing increased randomness in the system. Thus, heat Q has randomizing influence on the system. Can we then equate delta S with Q weight? Experience suggests us that the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it than one at lower temperature. Thus, temperature is the measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than the same quantity of heat is added to its high temperature. This suggests that entropy change is inversely proportional to the temperature. Delta S is related with Q and T for a reversible reaction as delta S equal to Q reversible upon T. The total entropy change for the system and surrounding of a spontaneous process is given by delta S total equal to delta S system plus delta S surrounding greater than 0. When a system is in equilibrium, the entropy is maximum and the change in entropy is 0. We can say that entropy for a spontaneous process increases till it reaches a maximum, and at equilibrium the change in entropy is 0. Since entropy is a state property, we can calculate change in entropy by delta S system equal to delta S system dot reversible by T. We find that both for reversible and irreversible expansion for an ideal gas under isothermal condition, delta U equal to 0, but delta S total, that is delta S system plus delta S surrounding, is not 0 for irreversible processes. The delta U does not discriminate between reversible and irreversible process where delta S does. Gives to energy and spontaneity. We have seen that for a system it is a total entropy change delta S total which decides the spontaneity of the process, but most of the chemical reactions fall into the category of either closed system or open system. Therefore, for most of chemical reactions there are changes in both enthalpy and entropy. It is clear from the discussion in previous section that neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous changes for the system. For this purpose, we define a new thermodynamic function, the Gibbs energy or Gibbs function G, as G equal to H minus Ts. Gibbs function given extensive property and a state function. The change in Gibbs energy for the system delta G system can be written as delta G system equal to delta I system minus T delta S system minus S system delta T. At constant temperature delta T equal to 0, therefore delta G system equal to delta H system minus T delta S system. Usually the substrate system is dropped, and we similarly write the equation as delta G equal to delta H minus T delta S. Thus gives energy change, enthalpy change minus temperature into entropy change, and is referred to as Gibbs equation, one of the most important equation in chemistry. Here we have considered both terms together for spontaneity, energy and entropy. As indicated earlier, dimensionally if we analyze, we find that delta G has units of energy because both delta H and delta S are energy terms. Now let us consider how delta G is related to reaction spontaneity. We know delta S total equal to delta S system plus delta S surrounding. If the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in the enthalpy of surrounding. Therefore, entropy change of surrounding delta S surrounding by T minus delta equal to minus delta H system by T. Delta S total delta S system plus minus delta delta S system plus minus delta H system by T. Rearranging the above equation, T delta S total equal to delta S system minus delta S system. For spontaneous process, delta S total is greater than 0. So T delta S system equal minus delta H system greater than 0. Using equation, the above equation can be written as minus minus delta G is greater than 0. Delta G equal to delta H minus T delta S. Delta H system is enthalpy change of a reaction. T delta S is a reaction which is not able to do useful work. So delta G is the net energy available to do work, and is thus the measure of the free energy. For this reaction, it is also known as the free energy of the reaction. Delta G gives a criteria for spontaneity, constant pressure and temperature. If delta G is negative, the process is spontaneous. If delta G is positive, process is non-spontaneous. Note, if a reaction has a positive enthalpy change and positive entropy change, it can be spontaneous when T delta S is large enough to outweigh delta H. This can happen in two ways. The positive entropy change of the system can be small, in which case T must be large. The positive entropy change of the system may be large, in which case T may be small. The former is one of the reasons why reactions are often carried out at high temperature. Entropy in second law of thermodynamics. We know that for an isolated system, the change in energy remains constant. Therefore, increase in entropy in such system is the natural direction of a spontaneous change. That in fact is the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In exothermic reaction, heat released by the reaction increases the disorder of the surrounding, and overall entropy change is positive, which makes the reaction spontaneous. Absolute entropy in third law of thermodynamics. Molecules of a substance may move in a straight line in any direction. They may spin like a top, and the bond in the molecule may stretch and compress. These molecules of the molecule are called translations, rotational and vibration motion respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lowered, entropy decreases. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolutely zero. This is called the third law of thermodynamics. This is so because there is perfect order in crystalline at absolute zero. The statement is confined to pure crystalline solid because theoretical arguments and practical evidences have shown that entropy of solution and supercooled liquid is not 0 at 0 Kelvin. The importance of the third law lies in the fact that it permits the calculation of absolute values of entropy of pure substance from thermal data alone. For a pure substance, this can be done by summing Q reversible by T increments from 0 Kelvin to 298 Kelvin. Standard entropies can be used to calculate standard entropy changes by Hess law type calculation. Gives free energy and equilibrium. We have seen how a knowledge of the sign and magnitude of the free energy changes of a chemical reaction allows prediction of the spontaneity as a chemical reaction, prediction of the useful work that could be extended from it. So far we have considered free energy changes in irreversible reaction. Let us now examine the free energy changes in reversible reaction. Reversible under strict thermodynamic sense is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surrounding. When applied to chemical reaction, the term reversible indicates that a given reaction can be proceed in either direction simultaneously, so that a dynamic equilibrium is set up. This means that the reaction in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So the criterion for equilibrium A plus B equilibrium C plus D is delta G equal to 0 gives free energy for a reaction in which reactants and products in a standard state. Delta GR is related to the equilibrium constant of the reaction as follows: 0 equal to delta GR plus RT ln K, or delta G equal to minus RT ln K, delta G equal to minus 2.303 RT log K. We also note that delta G equal to delta H minus T delta is equal to minus RT ln K. For strongly endothermic reaction, the value of delta HR may be larger and positive. In such a case, value of K will be much smaller than one, and the reaction is unlikely to form much products. In case of exothermic reaction, delta H is larger negative, and delta G is likely to be larger negative too. In such case, K will be much larger than 1. We may accept strongly exothermic reaction to have large K, and hence can go to near completion. Delta G also depends upon delta Rs, and the changes in the entropy of reaction is also taken into account. The value of K or extent of chemical reaction will also be affected depending upon whether delta S is positive or negative. From the above equation, it is possible to obtain an estimate of delta G from the measurement of delta H and delta S, and then calculate K at any temperature for economic yields of the product. If K is measured directly in the laboratory, value of G at any other temperature can be calculated. So this was all about our chapter thermodynamics. Here we have covered the first law, second law, and third law, and all the terms which are used in thermodynamics. Yeah, thank you all for watching the video. Like and subscribe to my channel for more such videos.